Hello everyone, my name is Hossein Darvishi and I'm a PhD student with Signal Processing Group in Electronic Systems Department of NTNU, Norwegian University of Science and Technology. And I'm here to present our paper titled A Data-Driven Architecture for Sensor Validation based on Neural Networks on behalf of my colleagues Domenico, Ciuonzo, Eivind, Rosón, Eide, and Pierluigi, Salvo, Rossi. Before I start presenting the paper, I need to mention two things. The first one is that this paper has been presented to IEEE Sensors 2020 conference, and also this project is partially supported by Research Council of Norway under the project Signify within the IKT Plus framework. So let me share my screen and start presenting. Okay. First of all, I'm gonna give you a brief introduction to the main problem with sensor, which is faulty sensors, and also the solution, which in general called sensor failure detection, isolation, and accommodation. And then I'm gonna present our own architecture for this problem in a more specific way. And then we have the simulation result, and finally the conclusion. Well, sensors are the drivers of Industry 4 and Internet of Things in many factories and many other workplaces, and also in our houses. So within this concept, data systems are very dependent to the data collected by these sensors. But the problem is these sensors are not perfect, and sensors are prone to error, and corrupted data from the sensor with failures may negatively affect both simple and more advanced functionality of the system and result in overall system performance degradation and increased risk level, which this would lead to consequences ranging from financial losses to critical safety issues, including life losses. The general solution to this problem called sensor failure detection, isolation, and accommodation, which this SHEM is performs three main tasks, which is detection, which is detecting a fault condition within the system, and isolation, which stands for identifying the faulty sensor, and finally accommodation, which is replacing the faulty data with some other trusted data. All the research in this field and the solution can be categorized into two groups, two main groups. The first one is model-based methods, which, as you may know from the name, these methods are are dependent to the model of the system. And for some complex models, it's going to be very difficult to precisely model the system. And that's why the second group have been gained more attention in the recent years, which they are called data-driven method, which they are not dependent on the model of the system. And our proposed architecture is also falls into this group. So here we have our SFDI architecture figure. We have it here on the right side of this slide. And as you can see, as a first step, we separated the reliable sensor and unreliable sensor, which unreliable sensor stands for sensor which are prone to error. And our proposed architecture are contained of three layers, which the first layer is the estimation layer. The second layer is the error computation layer or residual layer. And the third layer is classification layer. In more specific manner, in the estimation layer, we have NU estimators. NU is number of unreliable sensors. And since we are estimating the values of each unreliable sensor, we call these estimators virtual sensors. So each virtual sensor is a classic multi-layer perspectron, neural network, which its input is sensor data from all sensors except the sensor underestimation from time n to n minus m, just like a sliding window mechanism, just to help neural network to exploit the temporal coloration in the data. And also the output is the estimation of sensor underestimation at time n. So the output of the estimators or this virtual sensor are used in the next layers of our architecture, and also they are used to perform accommodation tasks since they are presenting a reliable replacement for faulty sensors. So at the classification layer, again, we also have a MLP classifier with the softmax layer output, which performs two tasks of detecting and isolating of faulty data. And again, the input of this signal is error vectors or error signal, which is the subtraction of the estimator values and the real values as at the second layer at time instant of n to n minus k, which again, we have the sliding window mechanism just to exploit the temporal correlation here as well. So the output of the classifier is a decision vector output of the class softmax layer output. So the softmax give a vector containing elements, which each element presenting probability of that class to happen, which each class in our method is presenting one of the sensor is faulty or not. So it gives us a probability about that sensor is faulty or not. So we're gonna have NU outputs, but here we have NU plus 1 output because that plus 1 is because we have considered the non-case as well, just like none of the sensor is faulty, just to perform the detection task. So since each of the element contain a value between 0 and 1, which is the probability of that case to happen, and D0 is representing the non-case. So the maximum element representing the decision of the classifier. So detection task performed with if the IM equal to 0 or not, which is if it equal to 0, that means the case 1 was, case 0 was happened, and case 0 performing the non-case, which none of the sensor is faulty. And if it was any other number rather than 0, that means isolation task, which it's referring to that sensor to be faulty. So that's how the architecture works in the simplest way to mentioning it. So here we have the simulation result. For simulation, we use the public available data set, which is called air quality data set with 5 metal oxide chemical sensor. And we consider all those 5 sensors as unreliable sensors here. And also we consider the temperature and humidity data as reliable data. So the data is divided to the testing and training. 50% of data is kept for testing purposes, and also 50% of the training data set is considered for validation purposes, just to make sure the MLP's neural network is not gonna overfit during the training step. And to assess the performance of our method, we consider weak bias fault, which stands for 20 to 40% of the value of each sensor as a bias fault, which is added significantly to the data set to assess the performance of our proposed architecture. And here we have the output of different stages of the proposed SFDI architecture for bias fault over 1 week of the test set. as you can see, the figure A, the part A of figure 1 and 2 are the same. They are monitoring the fault under different sensor where, as you can see, the proposed architecture is successfully detecting and identifying all faults without any delay. As you can see here, none of it. The blue line is the actual faulty sensor, and the dashed line, the dashed red line, is unidentified faulty sensor. As you can see, as the fault is happening, the sensor detecting it promptly. So, the B part of figure 1 and 2 are presenting the output of the virtual sensor and real output of each of the unreliable sensors. For example, here at day 5, we have fault on sensor NOx, which here we have signal for NOx, which as you can see, the purple line is the final output of the control system. And at this point, which fault happens, the blue line is the real value measurement with a fault including. As you can see, since here we have the fault, the purple line starts to map to the yellow dashed line, which is the virtual sensors at the first layer output. So here we have detection and we have accommodating task. We can see it here. And another point at the figure, at the part A, which I forgot to mention, is that system is successfully detecting and isolating all of the fault in the system without any delay, and only two fault is we have only two false decorrelation sample, which is also called as false positive, in the second day and the fifth day. So here we have the normalized confusion matrix on the test set. The confusion matrix again shows excellent accuracy of the proposed architecture. For example, the diagonal of the matrix representing the correct classification per each class. And as you can see, all classes show high precision, over 90%, with the lower precision exhibited on O3 and NOx sensors, with values of 93.75% and 93.64% respectively. In general, we presented our machine learning based architecture for SFDI HM. And in our method, we exploit both reliable and unreliable sensor, and also the temporal correlation between the sensors. And we show that our method is able to promptly detect and isolate and accommodate the faulty data. And detection performance on average have been reached 97.4%, which is remarkable. And for future, we're gonna try to work on a deep network structure instead of using simple MLPs for futures. So that was it, and thank you so much for watching this video.